So we're going to start with a little thought experiment for lesson 6. Here's our thought experiment. Imagine a person is standing on a ramp, standing on a Newton scale that's on the ramp. So the scale measures in newtons, just to make our math easier, attached to a rope. As the angle of the ramp increases, what happens to the scale reading? No change, increases, or decreases? What do you think? Well, first of all, I'm really not asking you to tell me about the scale reading. When I say scale reading, what force am I really talking about? Normal force. Okay, so really this question is saying, what happens to the normal force exerting from the ground up through this person? No change, gets bigger, or gets smaller. What do you think? Shaq, you had a suggestion? Oh, I thought you whispered an answer. If they give me a thought experiment like this, Mickey, one of my strategies is to imagine what's happening at the extremes and then think how I got from one extreme to another. In other words, I'm going to imagine we're flat. I'm going to imagine we're vertical, because that's the steepest we could get. And I think I have to get there smoothly. So if we were flat, if we were not tilted at all, what would the scale read for normal force? mg. If we were vertical, so that he was dangling, what would the scale read for normal force? Joseph's shaking his head. As a number, what would it read? 0 newtons. So if we go from mg to 0 newtons as we get steeper, what do you think? No change, increases, or decreases? How can we do that smoothly? You're right. Louder. It's got to decrease. Maximum is when you're level, minimum is when you're hanging, and it's got to be smooth. It can't suddenly magically change. So you know what? Decreases. In fact, in my answer, I'm going to say when level, Fn equals mg. When vertical, Fn equals 0. How would you go from mg to 0, from maximum to 0? I guess you're decreasing. Therefore, decreasing. Something like that. Something like that. Is that okay, Jordan? Okay. By the way, friction is what times what? So, as a hill gets steeper, what happens to the normal force? Gets bigger, smaller, or stays the same? Smaller. What happens to your ability to stay on the hill with friction? Bigger, smaller, or stays the same? This is why the steeper a hill, the harder it is to stay on it. Which seems really obvious. Well, duh, I can't stand on a wall. Yeah, but this is the physics of why. Okay. Same example. As the angle increases, hey, what happens to the tension in the rope? No change, increases or decreases. I bet you can figure it out using the same methodology that we just used. Think about level, think about vertical, think about when is the tension the most, when is the tension the least, and how would I get there? What do you folks think? Increases. Because vertical, if the ground is flat, what would the tension in the rope be? It'd probably be hanging because it'd be essentially 0. And vertically, oh, I can tell you what the tension in the rope is exactly equal to if I'm not accelerating. What's the tension in the rope? mg. Oh, yeah. So you know what? Increases. Explain your answer? Okay. Same as before. I'll write it this time. When level, t equals 0. When vertical, T equals mg. Therefore, T increases. Normal force decreases, tension increases. Okay. Let's continue to think about being on a slant. What the previous example shows is that for objects on a ramp, gravity is really doing two things. It pulls the object onto the ramp. Some people call that the squeeze force. And it partly pulls the object down the ramp. Say, what? Here is our block. What are the forces acting on this block? Get the obvious one. Gravity in which direction? Straight down. Even though the ramp is slanty, that's going to be gravity. What we're going to argue is that actually I can break gravity up into components. I can break gravity up into a perpendicular component. Let's change colors, Mr. Dueck. And a parallel component. In fact, I call this mg, and my symbol, the symbol for perpendicular is an upside down capital letter T. I call it mg perp. And I call this mg, and the symbol for parallel is two slanty parallel lines. And right there is a lovely right angle. Pythagoras, Mr. Dueck. Pythagoras. SOHCAHTOA, Mr. SOHCAHTOA. And what we're really saying then, Zach, is this is what squeezes the mass onto the ramp. This is what pulls the mass down the ramp. In terms of other forces that act on this object, well, there will be a normal force. Now, a normal force is always at 90 degrees to the surface. Is this surface level? It's slanty. So here's the normal force. I'm trying to draw it perpendicular to the surface. Let me see if I can do a little better than that. I don't know the normal force. Oh, but look. I know another force the same size as the normal force, and it ain't mg. It's a component. And if the surface is rough, well, gravity's pulling it down. There can sometimes be friction pushing up, and that's how you keep your balance on a slope. So if you've ever walked like on a slanty roof or on something very, very slanty, gravity's pulling you straight down to the earth, but as a component, gravity is doing two things. It's pulling you into the roof, thereby increasing your normal force, but it's pulling you down the hill, and you have to have enough friction up the hill to cancel out down the hill, or you're going to slip. Example 3 says, draw a force diagram for an object on a rough, i.e. friction, ramp that is sliding A down the ramp. Okay. What are the forces acting on this block? Get the obvious one. What else? A normal force. Which way? Perpendicular to the surface. The normal force is going to look like that. Is there friction? Yeah, it said rough surface. Which way is this block sliding, Shaq, in part A? So which way will friction act? Nate, you're right. Up the ramp. The free body diagram would have those 3 forces. Now, if you wanted to solve it, you would break this one up into components, into a perpendicular and a parallel. I'm not going to write that on this diagram. We're going to be doing it a bunch upcoming. What if we were sliding up the ramp? Well, I would still have gravity down. I would still have normal force. But if we're sliding up the ramp, which way is friction acting? In fact, this object's going to come to a stop pretty quickly. Next page. Example 4 says, which of the following is the best force diagram for a mass that is at rest? I'll underline the word at rest. That's a key physics word. A or B? And convince me. What we're going to be doing, Mickey, from now on is if they give me a ramp, we're going to break every force up into perpendicular and parallel components. Now, this force here, this one, Mickey, is already perpendicular. I'm okay with it. This one here is parallel to the ramp. I'm okay with it. I don't like this. I don't like this. So we're going to break it up into components. And if you look at it that way, one of these diagrams is impossible for it to be at rest. Because in one of these diagrams, you have a net unbalanced force. A or B? Josh? B. Why B? You're right. Well, let's see. It turns out in B, the normal force and that component cancel each other out. So I can be at rest in terms of sinking into the ramp like quicksand or flying off of the ramp like Superman. But I have part of gravity pulling it down the ramp. Sabrina, do you see any force at all pushing back up the ramp? B can't be at rest. Got to be A. Oh, it wants which one is at rest? A. And I really used Newton's first. I said that has balanced forces. But really I did it, Rachel, by looking at B and saying that one can't possibly be at rest because it's a force down the hill and no force up the hill. In A, by the way, our equations would be these 2 forces are the same and these 2 forces are the same. In order to find the size of the squeeze and slide components, we need to find the angle. What we're going to do, Mick, is we're going to draw every one of our diagrams identically. I'm just going to decide that. You don't have to, it's not wrong, but because I want my diagrams to all look the same, and that way if we always draw them identically, we're actually going to be lazy and memorize where the angle goes. I'm going to do a proof with you once, and then we're going to say, yeah, it always goes there. So whenever they give me gravity down, like this, I'm always going to draw the perpendicular first and then the parallel, always. And you're going to see me do that for the next year. If that's the case, you ready? We're going to do a proof. So angle 1, how big is this angle right here? Look at the picture. How big does it look? Okay, 90 degrees. Why? Because gravity is perpendicular to the horizontal ground. Okay. How big is angle 2? Now, you ready? I'm going to say angle 2 is 90 minus theta. Now, why can I say that? What does every single triangle add up to? 180. If this is 90, what's left for these 2 guys to add up to? Also 90, right? So whatever theta is, that's going to be 90 minus theta. If this is 50, I'm telling you, that's 40. If this is 20, that's 70. If this is theta, it's 90 minus theta. So far, so good. How big is angle 3? Now, in Foundations of Math 11, I know you do this. I don't know if you do this in Pre-Calculus 11. See the Z? See the Z? Angle 3 is the same size as angle 2. Do you guys do that in Pre-Calc 11 at all? Do you need doing geometry anymore? Stupid. They should never have nuked it, but they did. It's called alternate interior angles, but trust me, it is. And there's lovely proof to it. Now, you ready? Here's our final conclusion. How big? How big? How big, what angle is angle 3 the same as? So how big is angle 4? If this and this and this add to 180, what do this, this, and this have to add to? If those two are the same and those two are the same, what can you tell me about that? What we're going to do from now on, Joseph, in all of our diagrams, what we're going to do from now on is we're going to go scribble right here and scribble right there, and we're going to say those two angles are the same. I'm just going to do that on the fly. I've done the proof once. This is one time I'm going to say, just memorize it. Show you what I mean. Let's do an actual example. Example 6 says, find the acceleration of a 2 kilogram mass sliding down a frictionless 25-degree angle ramp. I can do that. What are the forces acting on this block? Get the obvious one. mg. Trick of the trade, always put the mg on the same side as the pointy part of your ramp, the angle part of your ramp, and you'll see why in a second. What else? Is this block sinking into the ramp like quicksand? Is it flying into the air like Superman? So there has to be a force perpendicular called the normal force. Now, I drew it a specific length for a reason. What else? Is there friction? No. This is the free body diagram. The free body diagram would be that. However, we're going to now solve this. We're going to take gravity, mg, and we're going to break it up into mg perpendicular and mg parallel, where this is a lovely right angle and mg is the hypotenuse. And here's the proof that we just did, Zach. That angle right there and that angle right there are the same size. Okay. Which way are we accelerating? Straight down? It gives me a modifier. Down the ramp, okay? So who's winning? Down the ramp. Who's losing? Anything up the ramp. So look very carefully at my diagram and say, tell me who's winning. And don't say mg, because mg ain't down the ramp. Who's losing? And don't say normal force, because normal force ain't up. Is there anything up the ramp? Trick question. You know what? We need to do some trig. We need to get triggy with it. mg parallel, based on this angle right here, this side, opposite, adjacent, or hypotenuse. What about mg? Hypotenuse? Which trig function? Sine of 25 equals opposite over hypotenuse Can you get mg parallel by itself, please? Oh, sorry, I did two parallels. Whoops. Opposite over hypotenuse. Can you get the mg parallel by itself, please? Multiply the mg over. I get this. Are you ready? mg, two lines is sines. If you're looking for a stupid way, if you want to memorize it. Or you can just derive it every time. mg with two little lines, which is my symbol for parallel, is sines. I've given you the general one, the generic one, the one that'll always work. What is theta in this particular question, Nate? 25 degrees. Okay, so I went generic on you over here to give you the... So anyways, point being, my friend, oh, come on. Point being, I can now go mg sine 25 equals ma. Mickey, is there a mass in everything on the left-hand side? Mickey, is there a mass in everything on the right-hand side? What can you tell me about them, their masses, if they appear in every single term? Oh, look at that. The acceleration down the hill is going to be g sine 25. The acceleration is going to be 9.8 sine 25. 4.14 meters per second squared. Let's, you know what? Let's play around with this for a little bit. If the angle got bigger, would the hill be steeper or shallower? If the angle got bigger, would the hill be steeper or it meant to be really obvious? Be steeper. Do you think you would accelerate downhill faster or slower? Let's try, you know what? I'm going to do the same one with a bigger angle. I'll go sine, hey, what if the angle was 60 degrees? So you're telling me I should get an answer bigger than 4.14? Oh, yeah, I do. What if we were dead vertical? What angle would that be, first of all? 90. What would your acceleration be? Wouldn't you technically be in free fall? So, oh, you know what? Let's try that. Ha! What if you were flat? What would your angle be? 0. Would you accelerate at all then? So this is behaving. Remember I started out the very first question with the scale question at the beginning of the lesson? This is behaving in a way that makes sense. I think we've got the right setup. Let's keep going. I like example 7. I like example 7. I like example 7. Example 7 is a nice question. Says, consider a 5 kilogram mass sliding down a rough ramp. A, find the force of friction. B, find the acceleration. Okay. You know what this is a job for? Free body diagram. What are the forces acting on this 5? Get the obvious one. What else? Normal force. Put your pencils down. Don't write this next bit down. In my mind, Mac, right now, I already know that I'm going to break this blue one up into components, and it's going to look something like that. Something like that. You with me so far? Why did I draw my normal force that big? Why didn't I go that big, or why didn't I go shorter? Can you see which two forces are equivalent to each other? Which ones? That guy? Okay, so pick your pencils up, add a normal force, and in your mind, eyeball it so it's about that long. The same way on the previous question, when I drew the normal force, you can see I eyeballed it so it was about the same length as my perpendicular component. What else? Friction or not? Yeah? Which way is the block sliding? So which way is friction? There's my free body diagram. Now let's go components. And I'm going to break up gravity. I'm going to break up gravity into mg perpendicular component. Is that a phone? Yep. Okay, thank you. And mg, your timing is bad because this is the key moment right here. Draw that, please. Draw that, please. Oh, and then Mac, I'll also do that angle and that angle are this. If I always draw the perpendicular first, that proof that we did a couple of examples ago will always work. Okay. What does A want me to find? Okay. Friction is mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force, but it ain't no mg. What other force is the same size as the normal force? Do you see it? Mg perpendicular. Friction is going to be mu mg perpendicular. All right, what the heck is mg perpendicular? Well, let's do some trig. Mg, hypotenuse, right? Mg perpendicular, adjacent or opposite? Here's my angle. What's that? Adjacent? Hey, which trig function? Of course it is. Cosine of theta equals perpendicular over mg. Hey, how do I get the perpendicular by itself? So it's going to be mg perpendicular equals mg cos. So some students, because you're going to be doing this so often, choose to memorize mg with two lines parallel is going to be sine, if you always draw it my way. And then they say, oh, mg perpendicular is the opposite of sine, cos. Or some students, Rachel, just go as far as putting the a there and they go, oh, adjacent cosine. And they go just as far as putting the o there, opposite sine. And they memorize that as their shortcut. Okay? So, if we plug this all in, we're going to get friction is going to be mu mg cos is going to be 0.2. Oh, Mickey, is there a mass in everything this time? I got an M here. Do I have an M in here? Do you see an M right there? So does the mass cancel this time? Nope. What was the mass? 5 times 9.8 times the cosine of 35. I left lots of room. Yes, I did. Good. Point 2 times 5 times 9.8 cos 35. I get a force of friction up the hill of 8.03. Is that right? 8.03 what units? It's a force. What did B want me to find? Acceleration, okay? I'm going to start out solving B algebraically. I could, because I found the force of friction, plug it into my equation. I'm going to leave everything algebraic because I just want you to notice how everything fits together. First of all, take a look at my picture. Which way is the block accelerating? Down, straight down? Down the what? Okay, then who's winning? It's got to be mg parallel, not mg, because that's in the direction of the winner. Who's losing? Is there more than one mass? No, equals ma. And I could, if I wanted to, Valoria, plug in the 8.03. I'm going to leave the friction algebraic for a reason. mg parallel. Opposite. Which trig function? Do you remember? mg2 lines is going to be sine. I can replace mg parallel with mg sine. And I'll just put a theta there. I'll stick the angle in later. Minus. Put your pencils down. Once you've written that. Naomi, friction is what times what? U times, don't write this down. I don't know the normal force. Oh, but look. I know another force the same size as a normal force. What? mg perpendicular. So I could say, okay, mg perpendicular. Wait a minute. We just said mg perpendicular was really mg what? Which trig function? Of course it is. So, you know what? Pick your pencils up. mg. Do you follow the reasoning I went through there? Okay. Equals what? ma. The reason I did this one algebraically, Mickey, my angel, is there an m in the first term? Is there an m in the second term? Is there an m in the third term? Then what say you? What can we do with these there m's there? Huh, well that's nice. So are you saying, Mickey, I actually already have the a by itself, I just got to plug and chug? Yeah. A is going to be g. What's that? 9.8. Sine theta, 35. Minus mu, 0.2. G, 9.8. Cos, 35. If this was vertical, what's the fastest it could be accelerating at? 9.8. If you get an answer bigger than 9.8, you've done something wrong. Crunch the numbers, what do you get? I typed something totally wrong. Oh, I missed a decimal right at the beginning, Mr. Dueck. Insert decimal. By the way, I didn't do that on purpose, but you saw I got the 40. I said, no, I can't be going faster than free fall. I'm still wrong. Okay, let's try this again. Oh, I missed a decimal in front of the 2. Good gosh, Mr. Dueck. 2 mistakes. You get 4.015, 4.02? Is that right, finally? Units. What if you knew you typed everything in right, but you got a negative answer? What would that mean? What that would mean is, actually, friction was so big that this block wasn't able to start sliding. The same way as when you walk on the side of a slanty roof and you don't slide down, friction is big enough to keep you in place. It's not saying you're accelerating up. It's just saying, you know what? Actually, you're at rest. Turn the page. How many more am I doing here? I think 2 more. Good. A 7.5 kilogram block remains motionless on a surface that is inclined at an angle of 21 degrees. What's the minimum coefficient of friction on the surface? You know what this question's asking me to find? What's mu? I don't know what's mu with you. What's mu, right? Can't do these in my head. There's my ramp. Or you could draw it that way. I don't care, but I chose to draw it this way. Draw it a little neater than that. Here's the block. Okay. What are the forces acting on this block? Get the obvious one. By the way, if I can give you a little advice, if you want to get these wrong, draw gravity really short, because your triangle is your components are much tougher to draw. So you've noticing that I tend to draw gravity nice and long. In fact, often I'll go right through the baseline, because that also reminds me to hit it perpendicularly and helps me line up gravity. Oh, mg. What else? What else? Is there friction in this question? Yeah? Which way? Well, which way does this block want to slide? Down the hill. And it does say that it's at rest, which means I think friction is up the hill. Is that okay, Zach? Good. Wants me to find mu. You know what? First thing I'm going to do is I'm going to break up gravity into its components. So I'm going to have mg perpendicular and mg parallel. And that angle and Sabrina, that angle are the same one, trust me. Oh, and you know what? It's a good idea to put the right angle there, because that makes it easier to spot the hypotenuse and avoid making silly, sloppy trig mistakes. Who's winning? Trick question. What word did I underline? So who's winning? It's a tie. It's a tie. Only, by the way, someone said friction. It's a tie because friction is only as big as it needs to be. So if you're not moving, friction is always tied, right? Let's pretend down the hill is the winner, because that's what we're most comfortable with. So I'm going to let down the hill be winner plus. I'm going to let, sorry, down the hill is that way for you guys. I'm going to let up the hill be loser minus. So who's winner plus down the hill? Which force? Can you see it? mg is wrong. mg parallel. Minus. Who's up the hill? Equals. Why did I put a 0 there? Motionless. In fact, if you were really clever, Josh, look up. You could have just done this. Right? I mean, you do that on the next line. I don't want to scare you, but so I'll bring the zeros back. Dope. Where am I? Right here, I hope. Okay. So next line I would say, and this is why I said it's a tie. Okay. mg parallel, look up. Opposite hypotenuse. Which one can we plug in for mg parallel? Which trig function? Sine. And you can remember 2 lines is sine, or Hopefully, Rafi, I just showed you another way that you can remember that it's sine just by doing the SOHCAHTOA, opposite hypotenuse. It's going to be mg sine, and I'll put a theta there. I know theta is 21 degrees, but I tend to do these generically and then plug in numbers after. Equals, friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What's the same size as the normal force? Sorry, I didn't hear. mg perpendicular. Which trig function can I replace mg perpendicular with? Well, I'm going to keep the mg, but it looks like this is adjacent. Oh, which trig function is the adjacent? Cosine. So I can actually go mg sine theta equals mu mg cos theta. What am I trying to find? What's mu? What's mu with u? How would I get the mu by itself? Okay, so mu, the minimum coefficient. By the way, the reason I said minimum coefficient of friction could be bigger. Maybe there's friction has room to spare, but you need at least this, or you're slipping. It's going to be mg sine theta all over mg cos theta. Mickey, is there an m on the top and an m on the bottom? Or on this line, Mickey, is there an m in everything? Then you know what? Mickey, is there a g on the top and a g on the bottom? Or in this line, is there a g in everything? It's going to be, what did I say the angle was? 21? Did I say 21? Yeah. What do you get? Who's in pre-calc 12? Have you guys learned that sine over cosine is also tangent? Okay. Turns out this is actually, the answer ends up being tangent. You don't know that yet, but that's okay. Right? If you go sine 21 divided by cos 21 and hit equals, if you go tan 21 and hit equals, the same thing. Cool. 0.384 units. What was that, Mickey? Not for mu, right? Now, Mickey, what was weird about this question? Not only did the masses cancel, but what else canceled? What that's telling you is this particular ramp, if you teleported it to Mars that has a different g, the block still wouldn't slide. Or if you teleported it to Jupiter, which has a different g than Earth, the block still wouldn't slide. It's saying this block would be stable anywhere in the universe, in any gravitational field in the universe. That mu will be enough to hold it in place. So you've actually found something universal, which is kind of cool. We're going to do this one on Thursday, but I'm going to give you some of the homework that you're now capable of doing. Didn't quite finish the lesson, but we came close. I think you can already try number 1. Number 2. Number 4. 4 is asking you to do it purely algebraically. Number 11. Nope, can't do 15 yet. So what have I given you so far? 1, 2, 3. I've given you 4. I'm going to give you a bunch more of these next class. But those ones are our first start. Also, any other missing homework, please get it in.